Today we are going to go ahead and just continue with some notes. You can see the topic up on the screen, but it's going to be called Antiderivatives and Indefinite Integrals, which I think sounds kind of scary maybe, but it's really not. It's going to be more of kind of laying down this foundation idea of some stuff that we need to know this semester. So the past 2 days we've been looking at Riemann sums, and I hope from yesterday you kind of picked up two things. One, how can we just find a Riemann sum? So like the LRAM, RRAM, MRAM, and then the TSAM. And then also being able to interpret if that approximation is going to be more or less than the actual value of the exact area under a curve, which is kind of what this whole idea of integral calculus is about. Today we're going to be talking about these things called antiderivatives, which are very much what they sound like. They're kind of like the opposite of a derivative. We're not going to really go into the exact area under a function today. We kind of need to build ourselves up to that. But basically these notes we'll do them today and then finish them up on Monday. Tuesday is going to be like a work day for you to finish up homework, and then you'll be able to ask any questions you have on that Tuesday, and then your first quiz is Wednesday. So looking at your notes again, follow along in OneNote if you wish, or however you want. The first thing before we begin is, of course, I do want to define what an antiderivative is or an antiderivative is. You can pronounce it either way. I do want to give you like the official calculus, very math sounding definition for it. I am going to use a notation that involves both capital letters and lowercase letters. So like just be careful when you're writing down the formulas for it. But we're going to say that f, and this is a capital letter F, is an antiderivative of lowercase f of x if and only if f prime of x, and that's the capital one, is equal to f of x. So what does all that mean? That's like a lot of f's in there, capital letters, lowercase letters. The main thing I want to think about when you're saying an antiderivative is you're kind of like undoing a derivative. So all first semester, pretty much everything that we did involved taking a derivative. The antiderivative is how do we go back to that original function. So a lot of these questions will be like, you'll have something that kind of represents the derivative, and we want to go backwards to find the original function for it. So one thing that we do want to be able to do is to identify and look for ways to notation-wise the antiderivative and things like that. And Angela, 1 second. I'm going to see if I can add you manually. I'll try that. So that is the definition of it. The first thing that I want to do is going to be just some examples of determining whether something is an antiderivative or whether something is not an antiderivative. So I have determined whether each function is an antiderivative of f of x, where f of x is equal to 3x squared. So the way that we're looking at this slide is I have three functions, and I want to ask kind of like, are those antiderivatives of this 3x squared? Or basically another way of saying that is 3x squared the derivative of one of those functions possible as an original function? Easy way to check is obviously just taking a derivative. So like if I take the derivative of that capital letter f of x, we get 3x squared. Well, 3x squared is clearly the same thing as 3x squared. So yes, that first one would be considered an antiderivative. We'll see a similar thing for that second one. If I have g of x, what is the derivative of g? That's going to give you 3x squared again. Where'd that 4 go? We know that the derivative of all constants is going to give you a 0. 3x squared is clearly the same thing as 3x squared. So this one, yes, is also an antiderivative. Where things start getting weird is this last one. So I have this h of x is equal to x cubed plus x. Taking the derivative of h, we get 3x squared. The derivative of x is just 1. Well, 3x squared plus 1 is not the same thing as 3x squared. They're close, but they're not the same. So this h would not be an antiderivative. Which brings us to kind of one big major idea with antiderivatives. And it's that there's going to be, for any one function, there's like a whole family of antiderivatives that could be possible. Could anyone think or describe like what would basically any antiderivative of that lowercase f of x look like? Or I might ask it this way, can anyone come up with another function that would also be an antiderivative of that lowercase f of x?
Well, it could be x cubed plus any constant.
Plus q plus any constant. I'm glad you worded it that way because that's kind of what I was looking for. So if we have x cubed plus any constant, that's basically going to be an antiderivative of 3x squared. Why would it make sense to say plus any constant? We know that the derivative of a constant is always going to go to 0. So for example, even if I chose something ridiculous like x cubed minus 10,000, that would still be an antiderivative of 3x squared because the derivative of x cubed minus 10,000 is still going to give you 3x squared. So we have this way in math of like, okay, so there's literally any number of antiderivatives we can find. So we do want to find a way to represent all antiderivatives. And how can we represent all antiderivatives? So I have this statement. If f of x is an antiderivative of lowercase f of x, then all antiderivatives can be expressed in the form of the antiderivative plus c. And we're going to use a capital letter here just kind of by tradition. And that plus c is going to represent a constant. We are going to see that plus c almost every day starting from now until the end of the semester. Anytime you do an antiderivative, actually let me correct myself, most of the times when you do an antiderivative, there's going to be a plus c there. And again, we need that plus c because if you think about it, when you undo a derivative, if there was a constant there originally, like you may not be able to know exactly what it was. So we want to have a plus c there to represent that there could have been a constant at the end of it. Yes, it could have been a negative constant, but that's the same thing as adding like a positive number. So what are some ways I can ask you to find an antiderivative? There's several ways right now that we're going to look at finding antiderivatives. I have 3 main ways we're going to focus on in this unit. The first way is for me to just say plainly, hey, what's the antiderivative? So like this first question, we say find all antiderivatives of this f of x is equal to 10x to the 4th plus 2x plus 3. What that means, if I kind of phrase it a different way, is we're kind of saying like, hey, this f of x is like the derivative. What would have been the original function that had the derivative with that 10x to the 4th plus 2x plus 3? I know we haven't learned any of the rules yet, but I think most of us are smart enough to kind of think backwards from the derivative to figure it out. Same with taking the derivative, we can do it like term by term. So like if I want to find the antiderivative of this, that first one is a 10x to the 4th. So you want to kind of ask yourself, the derivative of something is 10x to the 4th. And so that would mean the antiderivative of 10x to the 4th would be whatever that thing is you thought of. So the derivative of what would have given you 10x to the 4th? If you're thinking of it backwards.
Just 2x to the 5th.
2x to the 5th. Easy enough to check your answer. What's the derivative of 2x to the 5th? 10x to the 4th. And we can kind of do that term by term. So like looking at the next term, the derivative of something is 2x. So what is going to be the antiderivative of 2x?
X squared.
X squared, that's easy enough. What's the antiderivative of 3?
3x.
3x, and then what do we want to make sure we remember to put on the end of this? Plus c. And again, you're going to be a very sad calculus student if you leave a plus c off of your antiderivatives. And again, what that c represents is there could have been some constant, -1 plus 2 plus 20. and the derivative of a constant is 0, and that's why it doesn't show up in the problem. This second statement is asking literally the same question, just using a bunch of different words to do it. A differential equation in math is anything that has an equal sign in it and some sort of derivative. So if I'm looking at this statement, y prime is a derivative and there's an equal sign. So technically you're looking at a differential equation. Whenever you're asked to solve a differential equation, it's basically asking you to find the original kind of equation, if you will. So like if I say y prime is equal to 10x to the fourth plus 2x plus 3, when I say to solve that, you basically want to figure out what was the original y that had that as its y prime. Well, if we're going in that kind of backwards process, we are still finding an antiderivative. I was lazy and chose the same kind of polynomial. So this one would be y is equal to that 2x to the fifth plus x squared plus the 3x plus c. Questions so far about this thing called the antiderivative? All right, last notation that we can see, and then we'll look at some other rules, and this is probably the most important notation that we'll see, is something that's called integral notation. So we know in math, like if there's a way that we can use a symbol to say something instead of writing it out, like mathematicians are going to use that symbol. The symbol we use for finding an antiderivative is called the integral sign, and it's basically, imagine the letter S that's been stretched out. So it's super skinny, but it is the letter S. Also, we'll have something at the very end of an integral sign that will be written as dx for most parts. And I'll kind of explain what each parts of these mean as well. So again, this long S that you see is called the integral sign. It basically tells you to take the integral the verb for that is basically to integrate. Another way to say to integrate is basically to find the antiderivative. And that's why you'll kind of hear me use the integral and antiderivative interchangeably, because they really do mean about the same thing. The part you see in the middle, so this is what we're actually taking the integral of. It does have a proper name called the integrand. So it's going to be like a function or an expression that you are going to find the antiderivative of. And then this last thing at the end is not too important for us, but it does have to show up. Its proper technical term is called a differential. And what's important about it is that it tells you what your variable is. So kind of like when we did implicit differentiation, the dx tells you that you're doing it with respect to x. So like if your equation had like thetas in it, you would see a d theta. If it had t's, you would see a dt, etc. And what's kind of picky, and the AP exam's a little bit picky about this as well, is think of these as bookends. So like the integral tells you where to start integrating, and then the dx tells you where to stop. So everything between the integral sign and the dx is what's being integrated or what you're finding the antiderivative of. So I would read this out loud as the integral of 10x to the fourth plus 2x plus 3 with respect to dx. And what would that be equal to? That would be equal to 5, not that, try again, 2x to the fifth plus x squared plus 3x plus c. So kind of like the same way we did before, but that's just going to be the symbol way of showing the integral. Questions on that symbol, because we will be seeing a lot of it. All right, so let's go ahead and look at some of our rules. So when we first learned the derivative, we've learned that there's several derivative rules that you just have to know. And I often don't want to make integration rules that complicated. Like if you can take the derivative, then I don't want to say if you can take the derivative, you can take the integral, because it's not that easy. But if you know the derivative rules, then just think of them backwards, and that's going to give you the integral rule. For example, we have a power rule for derivatives. We know that if I gave you x to the fifth, you could easily take the derivative to give you 5x to the sixth. We know the power rule also works for fractions. Like if I have x to the 1/3, its derivative would be 1/3 x to the negative 2/3. How you wrote the power rule formula, just to remind you, we basically described it as that exponent came down in front as a coefficient, and then you subtracted by 1 in the exponent. So when we're thinking about the rule for integrals, it's going to be basically in reverse. Was there a question?
Yeah.
5x to the
Shouldn't
fourth.
the first one be 4? Fourth, yeah. Or to the
It's
fourth?
definitely no 100% before. Thanks. I'm getting ahead of myself. Yes, the integral one, you're definitely subtracting 1. Thank you. The integral, this is where I was getting ahead of myself. So for the derivative, you subtracted by 1, so don't be like me and mix them up. For the integral, you're adding 1. So you have to kind of think, if I'm integrating x to the fifth, you want to think like the derivative of something gave you x to the fifth. So like the original exponent would be, there's the 6, and then we're going to end up dividing by that new exponent. So I have 1 over the new exponent. Where that comes from, when I do the derivative of that antiderivative to kind of see how that cancels out and works, the derivative of 1/6 x to the 6, that 6 comes down in front, and those 6's cancel, giving you x to the fifth. Works the same way when you're doing fractions. So I'm going to add 1 to the exponent. 1/3 plus 1 is 4/3. 1 over that new exponent. And I would probably get used to, because that's a really ugly way to write it, 1 over a fraction just means rewrite it as the reciprocal. So we would have 3/4 x to the 4/3. Easy way to check your answer, take the derivative of that, and it will give you what you started with. The way we're going to write the power rule for integrals, so instead of subtracting 1, we're going to add 1. And instead of the original exponent coming down in front as a coefficient, it's the new exponent's going to be in front as 1 over it as a coefficient. Do have to be careful with one thing about the power rule, in that it doesn't work for one case, and that's when you have a -1. So it does work when you do the derivative, like -1 comes down in front, and that becomes x to the -2. It doesn't work when you do the integral, because if you add 1 to 1, you get 0, and then you have 1 over the new exponent, or 1 over 0. And in math, we can't divide by 0. That doesn't mean anything. So I'm going to kind of put a disclaimer here that n cannot be equal to -1 when you are integrating using the power rule. So basically, you can't have a -1 exponent. It actually involves an entirely different rule that we won't even get to until the next unit. So similar to with when we first learned the derivative rules, for a lot of the integral rules, you're going to have to sometimes rewrite it in order to kind of be able to use these rules. So I just have 2 examples, because I think people will pick up on it fast, especially since you've done the derivative before. To be clear, there is no chain rule for integrals. There is no power rule for integrals. And there is no quotient rule for integrals. Those are all for taking the derivative. So we're thinking about, we're like undoing those things, like those rules don't really have like a reverse button. So for both of these, you would want to basically find a way to rewrite it and then find the antiderivative. So this first one, there's no plus or minus, so you can distribute that cubed across. So we're going to have the integral of 8x cubed with respect to dx. Again, pretty easy using the power rule. Similar to derivatives, the coefficient's going to carry across. Add 1 to the exponent, divide by the new exponent, and then don't you dare forget your plus c. More than welcome to leave your answer like that. I would probably just in my head already, 8 divided by 4 is 2, and write my answer as 2x to the 4th plus c. But both of those answers are the same. Easy way to check your answer, take the derivative of it. The derivative of 2x to the 4th is 8x cubed. And of course, that constant's derivative would become 0. How would we want to rewrite that second one that we see?
8x to the negative fifth.
Yep, to the negative fifth. So again, no quotient rule. We don't want x to be in the denominator. So I would just rewrite it as 8x to the negative fifth dx. Don't forget that dx at the end of it. So 8's a coefficient, so it comes across. Add 1 to the exponent, divide by the new exponent, plus c. Could leave your answer like that, but it's really ugly. 8 divided by negative 4 is negative 2. That's how I would probably leave it. If this was the AP exam and multiple choice, they would probably write it like this as an option. But again, all 4 of those are equivalent, and I would give full credit for either of those 3 answers. So that's the power rule. I don't have a ton of examples with those because, again, if you can do the derivative power rule, then the integral rule kind of follows all the same steps. The last thing I wanted to do today, and this is where we'll kind of wrap up today's note, and then we'll finish the rest on Monday, is I say that the antiderivative, this process of integration, is the reverse of the derivative. So there are some trig rules, like, yes, you need to have these memorized, but technically you already have them memorized because you know the derivative rules, or at least you should know the derivative rules. And the 6 trig integral rules that you need to know, the 2 basic ones, we have the integral of sine and the integral of cosine. And how you know those rules, you want to kind of think to yourself, well, if I say the integral of positive sine of x is equal to something, in your head, just think of that as the derivative of something is positive sine. Well, the derivative of what is going to give you positive sine? And it would be negative cosine. And then don't forget your plus c. Easy way to kind of check it, when we do the derivative of negative cosine, I know that the derivative of cosine is negative sine, so we have kind of like the double negative, which is what's making that positive sine. So again, if you know your derivative rules, you technically know your trig rules. Likewise for cosine, if I say what's the integral of cosine, in your head you can ask yourself the derivative of something is cosine. The derivative of sine is cosine, so the integral of cosine would be sine of x plus c. Don't forget that plus c. The other rules that you technically know the rule for the integral of cosecant of x dx, the integral of secant squared dx, the integral of the product of secant times tangent, and the integral of the product of cosecant times tangent. Do want to talk about these before I fill it in. So again, like there's no chain rule or product rule for integrals. So like looking at that second line, like you're like, oh, this is something raised to a power, chain rule, but this is the integral. So kind of get the chain rule out of your head for integration. You just want to kind of think to yourself, hey, the derivative of something is cosecant squared. I know the derivative of cotangent is negative cosecant, so the integral of cosecant squared would be negative cotangent of x plus c. Then the next one, the derivative of what is secant squared? The derivative of tangent is secant squared plus the c. And then these last two, I'm going to do the secant one first. We know that the derivative of secant is the product of secant times tangent, and then cosecant times cotangent would be negative cosecant of x plus c. Quick hint, all the ones that start off with a co, all will have a negative when you integrate it. All the ones that have an answer that's not co will not have a negative attached to it. Questions on those rules, and make sure you have them written down. All right, so go ahead and try these last two, and this is where we're going to stop at today. Just 2 last examples. That first one will be using the product rule, have to rewrite it. That second one, no quotient rule, so you want to find a way to rewrite that second one so that it matches one of those 6 trig rules using some of your knowledge of trig identities. But take a moment to try those 2, and this is where we will wrap up today's notes. So this first one, if you're looking at it, it's the integral of the square root of t dt. Notice that the variable we're using is t, and that's why we see that dt there as opposed to dx. Square root of t is the same thing as t to the 1/2. Using the power rule for integrals, 1/2 plus 1 is 3/2. 1/3/2, and then don't forget your plus c. Most of you, I would hope, will just jump to this answer. 1/3/2 is just 2/3. And that's where the coefficient is. But technically, either of those answers would be correct. The second one, again, you want to force this to look like one of those 6 options. Those are the only 6 options we have for integrating trig. Of those 6, like I know I can write tangent as like sine over cosine, but if I'm looking at this one, I automatically, at least to me, this is going to be very, very similar to saying the integral of the product of tangent 1 over cosine is secant. And again, we have the d theta because that's going to be the variable. Well, the derivative of what is tangent times secant? The derivative of secant is tangent times secant. And of course, we have the plus c on that to represent any constants that would have gone to 0. Questions on antiderivatives and integrals? All right, so we're going to finish these notes on Monday because it kind of what we have left, I want to be able to do all in a single day. What is remaining is we're going to look at how we can actually go back and find that plus c. And then we're also going to go back and connect this to position, velocity, and acceleration from first semester. So kind of those are the 2 things we'll do on Monday. Your homework that I am assigning, this is homework 2. Looking at this, hopefully you've mostly finished that Riemann-Son homework. Again, I'm not really checking homework until that day of the quiz. So homework 1 and 2 are not due until Wednesday. You can go ahead and start this homework 2 now. You can probably do all of it except for that very last line. That's kind of what we're going to be covering Monday. But those first few problems, 7 through 10 all, and then 12 through 32 multiples of 4 are kind of like pretty quick, find the antiderivative. After the quiz is kind of where we'll pull Riemann sums and indefinite integrals together to see how we can use that to find the exact area under a curve. But with that being said, that's going to conclude the live portion of class. If you are good to go, then bye. Have a good weekend, and I will see you later. If you want to stay back and ask any questions, then definitely feel free to do that